In this video, I want to talk about conservative vector fields, and we worked with one of these in the last video without realizing it. The first example we did, there's our capital F. This is an example of a conservative vector field, meaning that there is a function out there in the world somewhere whose gradient is equal to this vector field. And we call that little function, lowercase f, the potential function of this vector field. So for now, the only way to show that a vector field is conservative is to actually go ahead and find that potential function. So our potential function, f of xy, is going to be 1 so that the gradient of that function is equal to our vector field. So what does that mean? That means that this vector field, its x component, is the partial derivative of my function with respect to x, and the y component is the partial derivative with respect to y. Okay, so let's think about that. If my f sub x is equal to 3x squared y plus 2x, I can integrate to figure out maybe what f is equal to. So let's do that. Let's find f. This is my candidate for f. So I'm going to integrate with respect to x, kind of work this backwards. So I would leave y and 3 as a constant. So I'll have 3 times x cubed over 3 times y. And then integrate 2x, we would get 2 times x squared over 2. And simplifying that a little bit, my 2's and 3's cancel out. So I might guess that my function is x cubed y plus x squared. But we have to be smart about this. Remember that there may have been some part of f that disappeared when I took the derivative. Remember, anything that only has a y in it, when I take the derivative with respect to x, it's going to completely disappear. So there could have been like a y to the 15th term here that when I took the derivative with respect to x, it would have just disappeared. So there might be some y stuff that's a part of this function that we can't see just by looking at this first component. All right, so here's where the second term in the vector field comes in. Let's look at that blue term. Our f sub y for this term is equal to x cubed plus 1. All right, so let's do the same thing here. Let's integrate with respect to y and see what we get. So this means that my function f might have been, see, x cubed is just a constant. We would stick a y on there. Integral of 1 with respect to y is just a y. And then we're going to recognize the same thing here, that we may have had some x stuff that disappeared when I took the derivative with respect to y. So I'm going to say there might be some x stuff here that would be part of the function. All right, so now we have to see if we can get the x column to agree with the y column. And if we can, we'll have a potential function and we'll have proved that f is a conservative vector field. All right, so I'm going to build my potential function over here. All right, so both the x column and the y column say that we need an x cubed y. They both agree that that needs to be there. So I'm going to put that into my function, x cubed y. Now, the x column says that I need to have an x squared. Now, the y column doesn't have an x squared, but it does allow us to put an x squared into the function because it says we could have had a bunch of x stuff. X squared is some x stuff, so we're allowed to throw that into the function. And then in the y column, it says that I need a y term. And in the x column, they say that's okay, because that's just some y stuff, and that could have been there. So I'm going to throw that y into the function. And this is our potential function. We've covered everything that both functions say need to be there. And if you take the gradient of that function, you will find that it's exactly equal to that capital F vector field. So why do we care if a vector field is conservative? If a vector field is conservative, it is what we call independent of path. And what it means is when we take these line integrals over vector fields, it doesn't matter what path we take to get from the start to the end of the curve. So we took the path y equals x to the 4th for this curve. And so what this is telling us is that we could have just drawn a straight line from the point 0, 0 to the point 1, 1, and we would have gotten the exact same value for our line integral. We also could have taken any path we wanted to. So we could have started here and we could have parameterized this very weird path to get to the end, and we still would have gotten exactly the same value for that line integral. So if that sounds a little bit fishy to you, you can go back and rework that example that we did in the last video. I used the parameterization of the curve to be t comma t to the 4th, and that took me from the point 0, 0 to 1, 1. So if you wanted to parameterize that straight line, you could parameterize t comma t. That would also take you from 0, 0 to 1, 1. And you could play around with any other curve that you wanted to, as long as it takes you from the point 0, 0 to 1, 1 along this vector field, you will get exactly the same value for that line integral every single time.